Okay, let's start my presentation. You can find the paper list and other information about me and my laboratory using this QR code. Okay. Sorry for this very busy slide, but our laboratory conducts several research topics regarding AD with high comfort, which is the main topic of this workshop. Which includes smooth control transition in control aspect using shared mode. Our method is to place the shared mode in which the automated driving system and human driver drive together between automated driving and manual driving modes to increase the stability of steering control and vehicle control. And another one is the teaching driver preferable trajectory. We know that the vehicle trajectory of AD affects trust of the human driver. And also we know that there exists individual difference in preferable motion. So we propose a direct teaching method to teach our preferable vehicle motion to the ADS, automated driving system. Okay, number three, helping to build appropriate mental model to fallback driver. We work on it because inappropriate mental model of the human driver could decrease the human control performance immediately after control transition. And yes, we're also working on increase of productivity during transportation using AD, such as reading tasks or working with laptop PC during transportation by reducing the motion sickness. And yes, as a basis of this project, we are working on the motion sickness estimation and its reduction by the experimental and modeling research. So I focus on this in this presentation. This slide shows a kind of advertisement of my colleagues' work. Another laboratory named Interactive Media Design Lab in NAIST also conduct research on the motion comfort of AD. The project is named XRM, Multimodal XR System on Autonomous Mobility, which is conducted by Professor Kambara and Dr. Sawabe. They produce this kind of nice multimodal XR system on AD, which includes immersive display like this with cylindrical screen or head-mounted display, and also and a motion platform is included to actuate a seat. And the purpose of this project is to make space comfortable. They are working on this to avoid motion sickness and diminishing sense of movement during transportation. Okay. Again, this is a kind of advertisement of my colleagues' work, but not mine. Okay, so let's start my own my themer from now on. Again, the title is Modeling Motion Sickness, and it's a potential application to the automated driving. As you know, level 3 or higher level of driving automation defined by say J3016, a driver becomes passengers. So subtask in the car will be increased. So there is a concern to increase the motion sickness during enjoying the AD. Let's consider about the original purpose of AD. That is I believe that is to release the driver, human driver from driving for reducing workload and increase productivity during transportation. So of course, the motion sequence should be removed. We have lots of research work which emphasize the importance of motion sequence in AV. These two are pioneer works. Number one, Diels and Boss pointed out concern of motion sequence in the context of the AV, such as seat location and the use of IT devices, etc. And introduced the design guideline for AVs for comfortable and productive ones. And Sibak et al. Conducted a survey regarding what kind of activity people want to do when in automated vehicles, and estimated increase of possibility of motion sickness. And I myself pointed out the importance of comfort in AD with emphasis on the vehicle control aspect. Okay. Quantification of the motion sequence is very important to develop countermeasures for reducing motion sickness. So so far, much effort has been made. For example, which includes questionnaire and biological signal measurement and computational models. So I focus on this computational model in this presentation. Okay, first of all, in my presentation, I mainly overview the computational model of motion sequence, including our recent activities. And then, in the final part of my presentation, I will discuss something about the potential application of the computational model of the motion sequence to the automated driving. Let's start to talk about the model of motion sickness. We have, roughly speaking, two kinds of models. The first one is the fitting model to describe the experimental results mathematically. The primary example is this ISO. And the advanced model based on this and multi-body dynamics multi-body dynamics approach has been developed by Salta et al. And another one is a model based on the hypothesis of mechanism of the motion sickness, which includes based on the sensory conflict theory and the subjective vertical conflict theory. Okay, let's start from this fitting model. MSDV is a standard method to estimate motion sickness for vertical motion, in which this frequency-weighted vertical acceleration is used to estimate the severity of motion sickness, like this. And the motion sickness incidence, which is defined as the percentage of people who vomit, is also estimated from this MSDV. This is an example. This is a relatively new model, which is based on this ISO. The input of the model is vehicle motion, visual condition, and the vehicle design. First of all, multi-body dynamics approach is taken to calculate the head movement from vehicle motion, and then the motion sickness score is calculated based on this ISO, and then the visual condition and individual differences are taken into account based on the fitting model approach. So this model successfully estimates the difference of the motion sickness severity by visual condition. So the size of the sphere represents the severity of motion sickness, And this figure demonstrated that the severity of motion sickness is smaller when sitting in a front seat. Okay. Okay, let's move on to the second types of model, the model based on the hypothesis of mechanisms of motion sickness. Sensory conflict theory is well-known hypothesis that the motion sickness is evoked by a conflict in sensory information. The cause of the conflict is thought to be modality and sensory information. For example, visual versus vestibular signals, and sensory information versus experiences based on our memory, and that which is described by internal model that is thought to be built in a central nervous system. As a pioneer work, Ullman developed a model of sensory conflict theory based on observer model approach, meaning that this is based on the internal model hypothesis. In this model, symptom of the motion sickness is generated by a discrepancy between sensory afference and expected one that is calculated by a forward model of the sensory dynamics. Again, yeah, here is the internal model of body dynamics, and here is the internal model of sensory dynamics. So these internal models are built in our thought to be built in our central nervous system. Okay. Questions we have in the sensory conflict theory is that what is conflict? Cause of the conflict. It is very difficult to answer, but only one exception is subjective vertical conflict theory, which is one of the branch of the sensory conflict theory. This theory defines the conflict as a discrepancy between the vertical direction sensed by our sensory system and estimated one built by our experiences, which is thought to be formed by our internal model. The big advantage of the SVC theory is that the model can deal with multidimensional and multiple source of sensory information. So the computational models of the SVT theory is actively researched. Again, the SVC theory is one of the hypotheses for which the computational model are being studied most actively. This table shows examples of the computational model of the SVC theory. This illustrates degrees of freedom and visual information, including visual flow and visual vertical, and the ability to deal with the effect of human motion prediction. Okay, and this, okay, just a moment. Okay, yes, yes, this is a very original one. Boston and Blaise succeeded to model SVC theory, which is a detail for 1 degree of freedom vertical motion, and then they also expanded this to include 6 degree freedom motion. We also proposed the SVC theory model that can deal with 6 degrees of freedom based on the canal otolith interaction. And yes, speaking of the visual information, Brasesi and Cianetti proposed expanded this 1 degree of freedom model to include the visual flow. And we also, expanded this 6 degree freedom model to include the visual flow too. In this in this paper. And also recently, this is a new one. I proposed I expanded this 6 COF model to include the visual vertical. Yeah, expanded this model to this, right? And yeah, in addition, recently I proposed a model here that can describe the effect of human motion prediction. In the following, I will explain some of them. These five: 1, 2, 3, 4, 5. This slide shows the first and the original SVC model, which is proposed by Boss and Bless, and data for the 1 degree freedom vertical motion, and which includes internal model by observer like the framework. The input of the model is actual head acceleration in vertical direction, and the output of the model is MSI, which is defined as the percentage of people who vomit. And this OTO represents the autolysis dynamics, and the first order log block is used to predict the vertical direction V. And this block represents the internal model of them, which is thought to be built in our central nervous system. And the C represents the subjective vertical conflict, which is error or discrepancy between this sensed vertical and expected one. And the accumulation of this conflict leads to the motion MSI, right? And the validity of the model was shown by a comparison with the experimental result. This figure shows the experimental result conducted by the Macaulay in 1976. In this experiment, subjects were shaken sinusoidally in a vertical direction for 2 hours, and this vertical axis denotes the motion MSI, and this axis denotes the motion frequency of the sinusoidal motion, and this axis denotes the amplitude of the sine wave. And this is the calculated estimated MSI by using this model. As you can see from them, we found that both figures have peak around this 0.2 Hertz, which is known as the most provocative frequency. Okay, we expand the SVC model to 6 degrees of freedom, including 6 DOF in rotation for the application to the automobile domain. The model includes the SCC, semicircular canals, as well as outlets, and its interaction to calculate the sensed vertical. And here is internal model to calculate the expected signals, including, of course, expected vertical direction. And here is a subjective vertical conflict. And again, the MSI is calculated as by the accumulation of this subjective vertical conflict. Okay, of course, the input of the model is the three-dimensional head acceleration and three-dimensional head angular velocity. Okay. Here is the detail of the 6 degree of freedom SVC model. These are the transfer function of the SCC or an autolith or something like this. But due to lack of the time, I'm omitting detail. Okay. So, the validity of the 6 degrees of freedom SVC model has been shown by the comparison with experimental data obtained by Macaulay in 1976. Again, okay, this is the experimental results again, and this is the calculated MSI by using our 6 DOF model. So again, you can find that both figures have a peak around this 0.2 Hertz, that is known as the most provocative frequency. We also compared the model output with experimental data for horizontal vibration. Griffin et al. Shook the subject laterally, in which the head could rotate. The vibration conditions are something like this. So they shook for 30 minutes. And they measured the instance of the mild nausea. So in order to compare the estimated MSI and the mild nausea instance, so we employ the normalized indices like this. Okay, so horizontal axis denotes the frequency, and vertical axis denotes the normalized MSI and normalized nausea instance. Okay, so as you can see from this figure, the both model fits this experimental result very well. And yes, for the low frequency domain, the 6 degrees of freedom motion, which includes the head rotation, fits better than the 1DOF model. Validity of the 6DOF model has been demonstrated in a variety of scenarios, including the vehicle passengers. So we also applied the model to analysis of the effect of the head tilt strategy on severity of motion sickness. Head and the vehicle motions were measured in slalom driving by using the IMU. The head motion of the driver and the passengers were measured by using the IMU, and also vehicle motion is also measured by using the same IMU. And the predicted MSI was calculated using the 6 degree of SBC model. The measured head movements were inputted to the model, and this is the result, and the predicted MSI. Yes, as you can see from this figure, the MSI of the passenger was significantly greater than that of the driver. Yes, now we have a question. What happens if the passenger imitates driver's head movement? Yes, we tested. The purpose of this experiment was to investigate whether the active head tilt of passenger, which imitates the driver's head, has an effect to reduce the motion sickness or not. This slide shows the experimental design. The participant sat on the passenger seat of a compact sedan and exposed to the vehicle motion. And yes, we have two head tilt conditions. The first one is natural condition, which means that the head moves along the centrifugal force. And another one is active condition, in which the participants were asked to tilt their head toward the centripetal direction, like the driver. And these two head tilt levels on 2 different days were conducted on 2 different days, at least 3 days apart. And of course, the order of the conditions were counterbalanced. The car was driven in an oval track like this, and with 2 slalom driving in straight lines. And here is the starting point, and at the end of each lap here, the participants were asked to indicate the severity of motion sickness according to the 6th level sickness rating proposed by Gordon. Okay, and when level 2, which means the initial symptom or higher, was observed or experienced, the driving trial was terminated at the end of the next lap. Okay. So each driving trial was terminated after 20 laps, even if the subjective rating did not reach 2 or more. This is the result. This figure shows the number of laps to the end point. Again, the number of this number is 20. So as you can see from this figure, this number of laps in the active condition is significantly larger than in that in the natural condition. And this is the vertical axis denotes the thickness rating by Golding. So the thickness rating in active condition is much smaller than significantly smaller than natural condition. So these results suggest that the active head tilt toward centripetal direction decrease, like a driver, decrease motion sickness. So I'm omitting here, but of course, the predicted MSI by inputting the head motion observed in this experiment showed that the predicted MSI was larger smaller in active condition than natural condition. We conducted another experiment to see the effect of the visual condition. So I'm omitting detail, but the results suggest that the effect of head tilt was significant. I mean, yes, this one. The head tilt toward centripetal condition reduced the motion sickness significantly. And in addition, the motion sickness was significantly larger in eye closure condition than eye opening condition. The 6DOF model presented so far does include only a vestibular input, but does not include visual information. So therefore, we added visual input to the original 6DOF model. The red parts here were newly added, which represent the visual flow input. By this input, the perceived motion is modified or altered. The structure of this part is based on this Newman's thesis. Okay. In the numerical simulation, we can directly specify visual input like this. To calculate, to calculate the predicted MSI using the experimental data, it is necessary to calculate this value, this visual flow, in some way. So we proposed a method to calculate this value from the visual image based on the optical flow analysis. I mean, the mean of the optical flow velocity across all pixels that exceeded the threshold was used as the visual velocity, like this. Okay, we conducted an experiment using the passenger car to see how the proposed model works. The participants were exposed to stop-and-go driving in navigator's seat. And the experimental factor is visual target, which includes looking forward condition and laptop condition. These figures show the relationship between the angular velocity of the head measured by IMU and that estimated by the camera image, right? In looking forward condition and in laptop condition. So as you can see from this figure, the correlation between them is high in looking forward condition, while the correlation was low in the laptop condition. Okay, and these signals are input to our proposed model, and the MSI was estimated like this. As you can see from this figure, the predicted MSI in the looking forward condition was significantly smaller than that in the laptop condition. This agree with Britsky et al. Result and our observation in our daily life. In the previous slide, visual flow was successfully introduced, but not visual vertical. When we estimate the vertical direction, we use our static visual information such as wall or floor. Such effect was incorporated into the previous model. Okay, the red part here is a red part were newly added in this model. The structure was also based on the Newman thesis. Okay, this part was added to here to get the better estimate of the perceived vertical direction, G hat, right? Okay, and this is firstly shown in this presentation. Okay, again, okay, let me check. The output of the model is the predicted MSI, and the input signals are three-dimensional head acceleration, translational motion, or gravity, and three-dimensional head angular velocity. Okay, and the visual flow based on the optical flow or something, and visual vertical, which was newly added in this model. Okay, this slide shows the simple simulation result showing how the proposed model works. In the simulation, visual information was vibrated in a sinusoidal way in roll direction like this, and while the body was not moved or stopped like this. Okay, this is a calculated result, time versus the predicted MSI. Okay, as you can see from this figure, the calculated MSI was increased like this, even though no body movement has been made. So we need to check we need to conduct experiment to check the value of the MSI, calculated MSI obtained here is appropriate or not, and to tune the parameters in the model. However, at least I'd like to say that the tendencies obtained here agree with our experience. Okay, let's move on to the next model that captures the effect of human motion prediction of exogenous motion. It is known that human predictability on exposed motion affects the motion sequence. For example, regarding the passive condition, repeatability or randomness of motion sequence, motion affects motion sequence. And upcoming visual information, such as road ahead, also affect reduce the motion sequence. And literature demonstrated that artificial audio or visual cues facilitate to reduce the motion sequence. And regarding the active condition, existence or absence of control activity is known to affect the motion sequence. Our 6-DOF model can deal with this phenomena, but no model can describe the human predictability in the passive condition of motion sequence. So we have newly built a computational model of motion sequence that can describe the effect of motion, human motion prediction. We assume that the humans learn dynamics of exposed motion when possible, and uses it to predict the motion in the very near future. We model this the dynamics of the exposed motion by using the nonlinear autoregressive model, in which the next motion is determined by the past motion. So by using this model, the assumption here can be rephrased that the human learn this function f, and the next motion here is predicted by this learned equation, right? Okay, this is a conceptual model describing describing the effect of human prediction of exogenous motion. This is based on the internal hypothesis. This is the block diagram block of the represented the body dynamics, and this is the sensory dynamics. And these are their internal models that is thought to be built in the central nervous system. And here is the estimated motion based on this internal model. And this signal is thought to be used to the body control, right? And the learning and learning and prediction mechanisms explained in the previous page is installed here to modify this estimated motion by incorporating this with reference copy related signals. Okay. And this facilitate to decrease the symptom of motion sickness. This slide shows concrete implementation of the concept and explained in the previous page. This model it's based on the both 1D wave model, but we assume that this 1D wave model can be directly expanded to the 6D wave translational motion. And the input of the model is head acceleration in the 3-dimensional space, and the output is MSI. And in this model, we added this red block to the boss 1D wave model, which is named the learning and the prediction of the exogenous motion to get the better estimate of the to perceived motion. Okay. For this block, the recursive Gaussian process regression model is used, and also this block outputs the predicted mean of the next motion, as well as the predicted this block outputs the predicted variance. This is a kind of the inverse of the confidence, right? And this variance is used to tune the weight of this signal, to calculate this signal. Okay. We compared the simulated result using our model with experimental data presented in this Kuiper's paper. Okay, in the Kuiper's experiment, participants were sat in this cart, and this cart was moved. And okay, there are 3 motion profiles. The first one is imprecaution, which denotes the predictable motion in which the cart was moved back and forth in the same direction. For example, forward and forward, backward, pause, forward, back, and pause, or something like this. Same direction and the same timing, right? And but okay, the second condition, DU condition, the direction is unpredictable. I mean, the direction of the pause was fixed, but the direction is unpredictable. So backward, 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 sometimes forward, or something like this. And the TU condition, the timing of the motion was unpredictable. I mean, the direction of is predictable, the forward back, or something like this. But the length of this pause was randomized. Okay. Okay, this figure shows the simulation result using our proposed model. From this figure, you can see that the calculated MSI using the proposed model demonstrated that the MSI in a predictable condition was significantly smaller than that in unpredictable motion condition, right? And this tendency agree with the Kuiper's experiments, right? On the other hand, the yes, conventional model cannot describe such differences, right? Okay. Okay, I'm omitting the detail, but our model can also describe the fact that the informative audio cue to represent the onset timing and the direction of the motion reduce the motion sickness, which revealed by the Kuiper's another paper. Okay.